All right, this one we'll be working BC homework 10.2. We'll be looking at parametric equations as they relate to like 2D motion. And there's going to be a lot of calculator questions. And like I told you in class, if you get one of these where they give you the components of the velocity, okay, which is basically what they're telling you if they give you dx dt and dy dt, you're going to want to load those into Desmos as f of t and g of t. All right, so over here I've got a Desmos window going, and I'm going to say f of t equals the square root of 3t, and g of t equals 3 cosine of t squared over 2. Okay, and then we probably aren't going to need the graphs of these. Who knows? We might, but if we want the velocity and acceleration vectors of the particle at time t equals 4, that's not going to require a graph, right? Now, if we've got a calculator, we might as well use it. So I'm just going to start. Okay, velocity vector is going to be dx dt at t equals 4 and dy dt at t equals 4. So f of 4 and g of 4. And okay, now that I've got those numbers, I'm going to go back over to the worksheet and say velocity is 3464 and negative 4.3 or negative 0.437. Okay, then I'm also going to say, I probably should have reported how I got those. So I'm just going to say x prime of 4 and y prime of 4. You don't have to write dx dt at. It's not totally necessary. Those are understood to mean the same thing. And then for the acceleration vector, we're going to be taking x double prime of 4 and y double prime of 4. If we're taking a derivative using the calculator, we definitely need to report that, right? That's calculus. So I'm just going to change it to a prime here to get the derivative of these things, which are going to be the second derivatives of the x and y positions. And that'll give me the acceleration. So the acceleration will be 0.433 and negative 11.872. Yeah, don't recommend loading these in as x prime of t and y prime of t because first of all, it doesn't like understand if you start off defining a derivative, and then second of all, it really doesn't like x and y as, or it really doesn't like x as a dependent variable, and I'm not sure about like y of x either. That it might not like that because it can graph implicit relations. It leaves me concerned. So okay, we've got those values. We're ready to move on. Oh, I mean, you didn't see me. Hold on, I'll show you. You didn't see me go in and type in the primes, but there they are, and that was how I got my results. All right. Okay, now we're going to do the position of the particle at time t equals 0. Okay, so we're just going to do that one component at a time. If we want to know the x component at time 0, and we know the x component at time 4, and the derivative of x, we can use the formula x of 0 equals x of 4 plus the integral from 4 back to 0 of the derivative of x. And so we're going to go back to the calculator and say that's going to be 1. Okay, so we see that right up there. But we'll go back to the calculator and then type in, ask for the integral, or maybe 1 plus the integral from 4 to 0 of x prime was f of t dt. Okay, and then I will report that value. Okay. Negative 8.237 or negative 8.238. And then we're going to need to do the same thing for the y component. Y of 4 was 5 plus the integral from 4 back to 0 of y prime which in the calculator we're calling g, so I should just be able to kind of edit the expression I'd already written, which would make sense because I'm doing the same thing just on the other component. Okay, so I can do that. It's going to report 1.601. This is part of why Desmos is such a big gain for us in AP Calculus. So, just like the speed at which we can do things is going to be really helpful. Okay, now, on the interval 0 to 4, at what time does the speed of the particle first reach 3.5? Okay, one thing I did recommend in some of my classes, but didn't remember to do in all of them, was to maybe after f and g define also an h of t function, which is the square root of f of t squared plus g of t squared. Okay. And, well, we are going to need the graph of that, actually, because it's asking us on the time interval 0 to 4. Okay, so I'm going to actually go in and restrict that, which is probably not something you would do if you were like taking a test, but just for the sake of the video, I think it's going to be helpful. But if it helps you to just restrict your field of vision to just that, that might be something you might be interested in. All right, so speed equals 3.5. So I'm going to also graph y equals 3.5. And it says the first time, so that's going to be right here. And I can just go ahead and label that. That's still visible to you? Yeah, 2.226. All right, but if I go back over here, if I just report t equals 2.226, I'm going to be leaving credit on the table. I'm not going to be getting all the points I could be getting. Okay, if we solve an equation using the calculator, we have to report which equation we solved. So speed equals 3.5. So I'm going to have something equal to 3.5, and speed is the square root of x prime of t squared plus y prime of t squared. All right, and that's the equation we solved, and that's our solution. All right, and then finding the total distance traveled by the particle over the time interval 0 to 4, we're going to integrate 0 to 4 on that speed function. So that's x prime of t squared plus y prime of t squared. If we go back to the calculator, that's just going to be integrating h of t from 0 to 4. You can get 13.182. So 13.182. All right. Now, okay, this one's no calculator. Particle moves in the xy plane, so the position is given by these two coordinates. Okay, so this is position. Find the velocity vector, so we're going to need to take the derivative. So the derivative of 2e to the 3t is going to be 2e to the 3t times 3 for the chain rule, plus e to the negative 7t times negative 7 for the chain rule, and then 9e to the 3t plus 2e to the 2t. All right, and find the speed of the particle at time t equals 0. All right, well, I'll find the velocity first. And so that's going to be 6 minus 7 and 9 plus 2. Okay, and that's going to be negative 1 and 11. Okay, so the speed is going to be equal to the square root of negative 1 squared plus 11 squared. And if you want to simplify that, you can, but you'd better be right. So 121 plus 1 is 122. Find dy dx in terms of t and find the limit as t approaches infinity of dy dx. Yeah, that's something different. Okay, so I've got the velocity vector, and that's going to be like the x derivative and the y derivative, so I'm going to say, all right, dy dx equal 9e to the 3t plus 2e to the 2t. Oh, that's a good problem. Divided by 6e to the 3t minus 7e to the negative 7t. And then as t approaches infinity, we need to think about the fastest growing thing on the numerator and the denominator. And that's going to be the e to the 3t. That grows the fastest of all, e to the 3t, e to the 2t, and e to the negative 7t. And so the limit as t approaches infinity of dy dx is going to be that 9 divided by 6. And so that would be 3/2. Okay. And then find each t value at which the line tangent to the path of the particle is horizontal, or explain why none exists. Okay, well, horizontal would be dy dx equaling 0. And that happens when the numerator of dy dx is equal to 0 and the denominator is non-zero. Okay, so it's not going to be happening. Okay, so that's looking for 9e to the 3t plus 2e to the 2t. Now, I am going to go back and double check, because like none exists is not that common of a thing to happen in this class. But for y, yeah, I'm going to have positive 9 and positive 2. Yeah, I'm resolute about that. Okay, so... Okay, that never happens, so... Let me think about how I would write this. Alright, let's grab this, move this around, get this out of the way too. Explain why none exists. If the path were horizontal, we would have dy dx equaling 0. But that is, it has no solution. I'm just going to say is not equal to 0 for all t. In fact, I might actually upgrade that to greater than 0. That's always positive. Greater than 0 for all t. So none exist. Okay. Find that each value of t at which the line tangent to the path of the particle is vertical. Okay, so that's going to be where the denominator is 0. That's going to have a place because there's a sign change. So 6e to the 3t minus 7. Making sure e to the negative 7t. I'm just going to once again double check those derivatives. Okay, so 6e to the 3t negative 7. Yeah, there's nothing. I was just hoping maybe I made an error that would simplify this, but it'll be all right. What can I factor out? Do I do the common denominator? Oh, definitely not. I'm going to add 7e to the negative 7t to both sides. This is kind of some complicated algebra. I like it. Okay, maybe I will multiply both sides by e to the 7t. Yes, that will be just the thing to do. And then, okay, so that's 6e to the 10t equals 7. E to the 10t equals 7 over 6, and you got it from here. 10t is going to equal the natural log of 7 over 6, and t is 1/10 of that. Wow, nice algebra. I haven't had any kind of that intensive in a while, so I think that's definitely something good for us to see. All right, now moving back to the calculator though. So we're going to go in and I'm going to clear out the calculator because I'm done with that other problem. Okay, and I'm going to actually type that in while I've got it visible on my other screen. So f of t is going to be dx dt sine inverse of 1 minus 2e to the negative t. Okay, and then dy dt is going to be 4t divided by 1 plus t cubed 4t greater than or equal to 0. Okay, great. Got F and G. Find the acceleration vector and the speed of the object at t equals 2. I don't see us needing it right there, so I'm just going to go ahead and leave that. Although the vertical tangent, maybe let me think about that. Oh yeah, where dx dt equals 0, so we might actually, yeah, that'll be a good thing for us to have eventually, but, part A, the acceleration vector and the speed of the object at time t equals 2 is going to be our I'm going to report that I'm taking x double prime of 2 and y double prime of 2. And that's going to be, right, bring in the calculator and say, all right, G for f prime of 2 and g prime of 2. Right, and yeah, if you wanted a fraction, you could click that button and get negative 20 over 27, but I don't see any reason to do that. If we're already reporting one decimal, I just report the other. 0.396 and negative 0.741. And then the speed of the object at time t equals 2 is going to be the square root of x prime of 2 squared plus y prime of 2 squared. Okay, I'm realizing you didn't see me right at that end, but okay, there you have it, and report what I'm plugging into the calculator. But I think, let me see, are we going to need the total distance? No, we're not going to need the total distance, so it's not going to be worth my time to program h of t. I'm glad I checked. So x prime of 2 squared plus y prime of 2 squared. The square root of f of 2 squared plus g of 2 squared. 1208. Right, now it says the curve has a vertical tangent at one point. Vertical tangent, that means that dx dt equals 0, or x prime. Okay, what time t is the object at that point? And that's where we'll go back to the calculator, graph dx dt, figure out where it equals 0. We can hold on to it if we need, but I don't think we'll need it past here. That's 0.693. Okay. Then we're going to let m of t denote the slope of the line tangent to the curve at the point x of t and y of t. Write an expression for m of t in terms of t and use it to evaluate the limit, just like we did on the last problem. So, all right, we've got dy dt. Okay, that's going to kind of be a lot. But maybe I'll just I'm going to just put 4t in the numerator and then 1 plus t cubed in the denominator. And then multiply by arc sine of 1 minus 2e to the negative t. All right. And then I will have... Okay, now let's think about this. How interesting. As t approaches infinity. All right. If that limit is going to be... Okay, now I'm going to explain why this is true, but I would not recommend, you don't need to get into this if this was like a question on the free response section of your test, or on the AP exam. I'm going to tell you why the limit of that is going to be finite, but it doesn't really matter because the 4t divided by 1 plus t to the third, with arc sine approaching, one particular value as t approaches, the arc sine of 1 minus 2e to the negative t is approaching one value as t approaches infinity. It's really just going to be the biggest growing thing on bottom is t cubed. The biggest growing thing on top is 4t. The denominator is growing faster. This limit's going to be 0. Okay, whoops. I'm saying that right now, but in case you're interested in that thing. Okay, so limit of arc sine of 1 minus 2 over e to the t. I might rewrite that in a way that's convenient for me to show you what's going to happen as t approaches infinity. As t approaches infinity, that fraction right there is going to approach 0. And so I'm going to be taking arc sine of 1. So that limit is going to equal arc sine of 1. Okay, now we could plug that into the calculator, but that's not probably the skill you need to be working on right now. Okay, we think about where on the unit circle is the most obvious place where sine theta equals 1. Right? Where is sine 1? It's the arc that represents sine equaling 1. That's up here at the top. That's pi over 2. Okay, so that's pi divided by 2. Right, and so the denominator is approaching 4t divided by 1 plus t cubed, whatever that's doing, multiplied by pi over 2 in the denominator, but the denominator is growing so large anyway, it doesn't matter, this is multiplied by pi over 2, the limit's going to be 0. All right, now we're going to say the graph of the curve has a horizontal asymptote y equals c. Right, but do not evaluate an expression involving an improper integral that represents this value c. Nice. I'm going to draw a picture for you. Let's say that's the y-axis. I've got this horizontal asymptote y equals c. So let me just make that thinner. I'm just going to say that's going to be the equation of the asymptote, or the graph of the asymptote, y equals c. I forgot what it was. I think it was 25. That looks right. And, okay, so I've got that. And the graph of the curve, we saw that the limit of dy dx was 0, so that makes sense that it's got a horizontal asymptote, okay, and that would be really giving away the answer in number 12 that I just read ahead. Okay, but let's see. What's happening with dy dt? I'm going to go back to Desmos and do a little investigation. As t approaches infinity, what's happening? Dy dt is positive. So y is increasing the whole time. And so I'm taking that to mean that we are approaching this horizontal asymptote from below. And so I'm thinking that more or less this curve kind of looks like that. So really what we're looking for is the limit of the y-coordinate. And okay, we've got the information about the position of the object at time t equals 2, the y-coordinate's negative 3. Okay, so y of 2 equaling negative 3. And we could say, what we're not going to say is y of infinity. Okay, hopefully you've been in my class long enough, you know that's the one thing you absolutely cannot do is plug in infinity as if it's a real number. I'm going to say c, which is what we're looking for, is going to equal negative 3 plus the integral from time t equals 2 towards infinity of y prime. Okay, now you could call it y prime. I called it dy dt, but 4t over 1 plus t cubed. Yes, and that's not an integral of the variety that we were expected to solve in this class, so that's where we're going to stop, right? And don't evaluate. Okay, I think it can be solved, but yeah, that form is... I'm not sure what the substitution would be, but I'm pretty sure it's possible. All right, so that's going to be all for that one. Okay, now we've got another calculator one. All right, so I'm going to load those equations into the calculator, f of t and g of t. Okay, I You can put in the domain restriction if you need, but I don't think it'll really matter to us. Find the speed of the object at time t equals 4. Okay, speed and then total distance, we're going to want to define h of t equals the speed in the calculator, not on paper, right? We're going to actually write the things in terms of the way they gave it to us. Speed will equal the square root of x prime of 4 plus y prime of 4. We don't have to, write in arctangent of 4/5 and log of 17 if we don't want to. But I suppose we could write it in like that and then leave it as, unsimplified, but, we're going to be using the calculator for all sorts of stuff here, and we're going to integrate total distance, or integrate the speed to get total distance, so we might as well just define the speed right here. So, whoa, and I definitely wrote that wrong, and I'll actually go back and fix that when I get back to displaying the calculator, or the sheet of paper. So, h of t is going to be the square root of x prime of t squared plus y prime of t squared, so f of t squared plus g of t squared. And then we're interested in h of 4, which is going to be 2.912, so 2912. Right, but now we have that issue. I did not square them right there, so I'm going to fix that and report my answer, 2.912. All right, and then we will find the total distance traveled by the object over the time interval 0 to 4. So we're going to integrate that, 0 to 4, the square root of x prime of t squared plus y prime of t squared. Integral from 0 to 4 of h of t dt, and that's going to be 6.423. And the position of the particle at time t equals 4. And x of 4 will equal, it told us the position at time t equals 0 up there, so I'm going to say x of 4 is x of 0, negative 3, plus the integral from 0 to 4 of the derivative of x. And I'll also set up the other one to save myself some time. The y-coordinate was negative 4, so negative 4 plus the integral from 0 to 4. But this time the derivative of y. No. Alright, so I just use this, negative 3 plus the integral from 0 to 4 of f of t dt. It's going to give me negative 0.892. And then what I'm going to do is I'm going to change that to g and this to negative 4 to get the y-coordinate, and that's going to be 1.984. Right. For t greater than 0, there is a point on the curve where the line tangent to the curve has slope 2, dy dx equals 2. At what time t is the object at this point? Okay, we already defined dy dx. No, we haven't. So I'm going to say what I'm actually solving is y prime of t divided by x prime of t. That's going to equal 2. Find the acceleration vector at this point. All right, so, okay, I'm not showing you the calculator. There we go. Okay, I might define a new function for slope s of t equaling dy dx is y prime was g of t divided by x prime was f of t. There's one point where this equals 2. So we're going to bring in the line y equals 2, grab that intersection point, report it down there, and bring it up. See it. And then it also asks, find the acceleration vector at this point. Oh, okay, so I am going to want that stored. Okay, so it's good that I clicked on that button. And I kind of did that without much thought, so I'm going to do that again. So you go over here to the intersection, you click it, and then you hit this button right here, and it exports the point to the expression list. It's kind of a new development on Desmos. It's really great. And what I like to do here is get rid of the rest of the stuff, keep that value, and define a new constant k. Okay, so that's going to be my constant, and now I'm interested in the acceleration vector is going to be the second derivative of f, which is going to be f prime, plug in k, and then g prime of k. And there I've got my acceleration vector right there, really quick. Okay, now I'm going to check back in with the paper. Okay, so I was just over here reporting the t value. So that's going to be t equals, that's k really, 1.357. But I used all 5 decimals, so I might as well report that. The reader's not going to look past 3, but it's good that we report what we do. All right. Now, you could say let k equal that, and then or x double prime of k and y double prime of k, but I'm just going to say acceleration is going to equal... maybe I would have been wise to x double prime of 1.357... ... and y double prime of 1.357... ... and that's going to be, okay, I'm just copying from the calculator, 0.135 and 0.955. Okay. Right, next, we've got a new problem. We've got x prime only, y prime not explicitly given. So I should probably type x prime into the calculator. I can clear out all the rest of this stuff. Yeah, maybe I could have kept h of t, but I guess it wouldn't have done me any good on this problem. So I'm clearing everything out. X prime is 2 plus cosine of t squared. And the derivative of y prime not given at time t equals 2. We've got the position of the object. Right. So it says find the x coordinate at time 4. We've got the x coordinate at time 2, so x of 4 equals x of 2 plus the integral from 2 to 4 of x prime of t dt. I'll just set all of these up and then go hit the calculator after. That's a strategy some people use. Get everything calculator ready and then go do all your calculations and then report your answers and move on. At time t equals 2, the value of dy dt is -7. Write an equation for the line tangent to the curve at x of 2 and y of 2. Okay, dy dt is -7. dx dt, now we could say is 2 plus cosine of 4. Yeah, that would be, you're okay to write it like that. Like, say you ran out of time on the calculator section and came back to it because you're allowed to do that. You're just not allowed to use a calculator. You could say that dy dx equals dy dt was -7. I'm probably not going to need that much fraction. It's very crooked. Divided by 2 plus cosine 4. Now I'm going to recommend we find that by actually just plugging into f of t when we get to Desmos. But the equation for the line tangent is going to be at, or we're going to have equation y minus 8 is equal to that slope multiplied by x minus 1, and we'll just fill that in and go hit the calculator. Speed of the object at time t equals 2 is going to be the square root of x prime of 2 squared plus y prime was a -7 squared. And we'll be able to calculate that. Now we could, again, if we had no calculator, we would be all right to write that as 2 plus cosine 4 and not use the calculator. And so really the only thing so far I've needed it for is the integral, but you do need it for the integral because 2 plus cosine of t squared is not something you can take the antiderivative of. And just then the line tangent to the curve has a slope of 2t plus 1. Find the acceleration vector of the object at time t equals 4. All right. Okay, so what they're telling us is dy dx at t equals 4 is going to equal 2 times 4 plus 1 is 9. Okay. We can say that x prime of 4. Wait a second. Find the acceleration vector. Time t equals 4. Remind myself how I've done this one in the past. Okay, I didn't look it up. I don't want to. I don't want to be stumped by one problem in my own homework. And I think it has to do with the fact that it's for all time t greater than or equal to 3. Okay, so I think, I think that fact that dy dx at t equals 4 equals 9 is going to be pretty much useless to us. I think we need to say dy dx, which equals 2t plus 1, is also equal to y prime over x prime. So that's y prime of t, yeah, divided by 2 plus cosine of t squared. That's still this problem, right? Okay, yeah, that's really something. So that's telling me that y prime, because I was like, I need something I can take the derivative of. Right, in order to get the acceleration vector. I can take the second derivative of x easily because it gave me x prime, but I needed something for y prime of t. Yeah, because again, just having it at one point is not useful at all. So 2t plus 1, or having the velocity at one point, multiplied by 2 plus cosine of t squared. Okay. And so now I've written down y prime of t, so I can really say, okay, my acceleration vector is going to be x double prime of 4 and y double prime of 4. And then I'll report those values. Okay, so I'm going to go to the calculator. Say, all right, first I need x of 4. So say x of 2, which was 1, plus the integral from 2 to 4 of f of t dt. That's 5.133. And so I'm going to report that over there. The next thing I need to do is do negative 7 over f of 2. Okay, so I'll do that. Negative 7 divided by f of 2. It's going to be negative 5.199. So I added that in as the slope of my tangent line. Next, I need to find the speed of the object at time t equals 2. So that's going to be x prime of 2 squared plus 49 in a square root. Oh, x prime of 2. I'm not thinking that's f of 2. Okay, but helpfully, Desmos told me I don't know what you're talking about. You have not defined that. So that's 7.128. Then I will keep going and plug in y prime of t. So I'm just going to call that, well, I guess first I'll find x double prime of 4. But I'm also going to plug in that y prime of t while I'm at it with the calculator. Okay. So I'm not going to need these anymore or that. So I'm going to say first I want f prime of 4. That's 2.303. I guess we get the second derivative of x. 2.303. And then I'm going to define g of t. Actually, because this is the last thing I've got, I'm going to add parentheses to this and multiply it by 2t plus 1. Okay. Have that, and then I just want the derivative of that at time t equals 4. That would give me 22.814. on to the last page, and it's been a pretty solid homework. Lots of good problems. So curve gamma is given by gamma of t equals t plus 2 over t and 3t squared for t greater than 0. Find the coordinates of each point on the path where the velocity of the particle in the x direction is 0. Right, so the velocity in the x direction is going to be x prime of t, so I'm just going to actually write that. X prime of t equals the derivative of t plus 2t to the negative 1. So 1 minus 2t to the negative 2. And coordinates of each point. Okay, so I'm looking for the zeros of this. So that's 1 minus 2 over t squared. Okay, so if t squared equals 2, then this is going to equal 0. And so I'm also, velocity in the x direction is 0. Okay, that's another way of saying there's a vertical tangent. Okay, so we've got this. This is great. T is going to either equal the square root of 2 or the negative square root of 2. I want the coordinates of the point on the path. So I'm going to say gamma at root 2 is the point. Root 2 plus 2 over root 2. That would be another root 2, and I could say that's 2 root 2, but that's just like kind of a lot. We don't need to simplify it. And then 3t squared is going to be 3 times 2. Okay, that's great. And then gamma of negative square root 2 is going to be negative root 2 minus 2 over root 2. And then another 3 times 2. All right, second derivative of y with respect to x. Okay, I've got x prime, I'm going to need y prime. I'm probably going to need to knock down the size of the pen too for this type of problem. There's going to be some writing. So I'm going to just kind of copy in my result. X prime equaled 1 minus 2t to the negative 2. Y prime is going to be 6t. 6 to the t. Just 6t. Okay. No calculator, huh? Alright. dy dx equals 6t divided by 1 minus 2t to the negative 2. Let me make sure I didn't do x prime wrong. But no, otherwise there wouldn't be any zeros. Whew. Alright. I hate to tell you, but there's nothing you can do to simplify that. At least that I know of. I suppose, well, I multiplied top and bottom by t squared. If you just want to take the derivative of this using the quotient rule and then divide by the same denominator, that's totally fine. Just see what happens. I might erase all this. 6t to the 3 divided by t squared minus 2. I could long divide that, but I'm still going to have a remainder. Okay, so either way, I'm going to have this fraction and like fraction, quotient, whatever. I don't really want to deal with it. Okay, so, or I don't want to deal with it in a more complicated version, so I'll just deal with it in the more simple version. So dx2 is going to be, all right, first I take the derivative of dy dx. Okay, so that's going to be bottom. For some reason, I feel like that's going to be better. Times the derivative of the top. Minus the top, okay, I'm going to need more fraction, times the derivative of the bottom, which is going to be 4t to the negative 3. Okay, all divided by the bottom squared, 1 minus 2 over t squared squared. Okay, that's the derivative of dy dx, and then I divide by dx dt again. So that's just going to give me another factor of 1 minus 2t to the negative 2 in the denominator. So I'm just going to kind of scratch through that and say that's a 3 now. All right, so that's my formula. I feel like I have done something wrong here, but I'm just going to stick with it. Okay, so when y equals 12, what is the value of t when y equals 12? That's going to be, okay, t is greater, oh my goodness. Okay, I'm noticing now that was kind of unnecessary there because t is greater than 0. I just didn't catch that. Okay, so 12 would be 3 times 4, t squared equals 4, that's t equals 2. All right. So, and you don't need to show anything for that. I'm just going to say, hey, I'm plugging in t equals 2. So 1 minus 2/4 is a half of 6 minus 6 times 4/8. That's another half. That's going to be 0, just provided that this thing is not 0. And, oh, goodness, like, okay, 1 minus 2/4, yeah, is a half cubed. Okay, so that's non-zero. At least, okay, that's the value of the second derivative. Massive letdown, but, you know, okay, we did the work. So find the position of the particle at time t equals 2. X of 1 is 5. Okay, we've got the xt. So it's going to be x of 1, which was 5, plus the integral from 1 to 2 of x prime. Okay, and this is just going to be an old-fashioned integral, so I'm going to add 1 to the power and divide by the new power. Not the natural log of t squared. You can check that by taking the derivative. The derivative of 12t to the negative 1 is going to be negative 12t to the negative 2. Okay, let t go from 1 to 2, so that's 12/2 minus 12/1. Oh, yeah, the velocity was negative. Okay, so, or the x velocity was negative, so x position is going to decrease. 6 minus 12 is negative 6. 5 minus 6 is going to be negative 1, but you could have stopped at the previous step. All right, find the slope of the tangent to the path of the particle at t equals 2. So I'm going to need dx dt at t equals 2, and that's going to be negative 12/4. And then dy dt at t equals 2. Okay, so that is the graph of dy dt, not y of t. Okay, I feel like I've seen one where they give you the x velocity and the y position, but it's obviously not this one. All right, so y prime of 2, that's going to equal negative 1. Okay, and so find the slope of the line tangent to the path of the particle at time t equals 2 dy dx at time t equals 2 is y prime of 2 over x prime of 2, which is going to be negative 1 over negative 3. That's a third. All right, and then the speed of the particle at time t equals 3. Oh, man, that's a shame. All right, at time t equals 3, okay, we're going to have to use the fact that this is a linear function. Okay, halfway between negative 1 and 0 is going to be negative half. Okay, so I'm saying y prime of 3 is negative 1/2. And then what I'm going to need here is negative 12/t squared. Negative 12/9, which is negative 4/3. Y prime of 3, I said, was equal to 1/2. And then the speed, let me clear about what I'm doing here. Speed equals the square root of negative 4/3 squared plus negative 1/2 squared. Okay, now you could say that's 16/9, 1/4. I mean, there's no point in doing it. But if you were going to do it, I think that's what it would look like. So, okay, that's going to be all for this video. That was a really solid problem set. Thanks for watching.